Today we're diving deep into the world of fast radio bursts.
SRBs.
FRBs, yeah.
Yeah.
These incredibly intense bursts of radio energy pack billions of times the power of pulsar signals, all within a fleeting millisecond.
Wow.
They're like cosmic lighthouses, blinking briefly but brilliantly,
Right.
carrying valuable information about the universe from billions of light years away.
Billions.
Our main focus today will be exploring how FRBs are helping us address the missing baryon problem and contribute to a deeper understanding of the universe's structure and evolution.
These millisecond bursts are indeed remarkable for the amount of information they carry.
Yeah.
They act as cosmic messengers traveling for billions of years, and their signals become imprinted with details of their journey through the cosmos.
Right.
This is what allows us to use them as probes to investigate the distribution of matter and the nature of the universe.
Before we delve into the missing baryons, let's start with a primer on FRBs themselves.
Okay.
What exactly are they and how are they detected?
Imagine a sudden, extremely bright flash of radio waves lasting for mere milliseconds.
Oh.
That's an FRB in a nutshell.
Okay.
They originate from outside our own galaxy, often billions of light years away, making them extragalactic phenomena.
Wow.
The first FRB was discovered relatively recently in 2007 from archival data collected by the Parkes Radio Telescope. As is often the case with groundbreaking discoveries, there was initial skepticism surrounding the authenticity of FRBs.
Sure.
But further detections confirmed their existence, leading to a surge in research within this field.
It sounds like detecting these FRBs is a real challenge given their incredibly short durations and unpredictable nature.
Oh, absolutely.
How do astronomers even manage to catch these fleeting signals?
You're right. Detecting and localizing FRBs is a considerable challenge.
Yeah.
Their millisecond durations mean that if we aren't looking in the right place at the right time, we'll likely miss them.
Right.
Furthermore, their seemingly random appearances across the sky make targeted searches difficult. To overcome these challenges, astronomers have developed specialized telescopes and surveys dedicated to finding FRBs.
What are some of the leading telescopes and surveys in this effort?
Several telescopes are playing crucial roles in FRB research.
Okay.
CSA in Canada, ASCAP in Australia, and the DSA in the U.S. are at the forefront of detection and localization efforts.
I see.
Each telescope has unique strengths, and their combined efforts are rapidly increasing the rate at which we discover and pinpoint these enigmatic bursts. CAA, for instance, has already cataloged hundreds of FRBs, and with the addition of planned outrigger telescopes, it's expected to further improve localization accuracy.
That precision and localization seems critical.
It is.
It's not just about finding them, but also about understanding where they come from so we can unravel the secrets they hold about their journey and the environments they've traversed.
Precisely knowing an FRB's location enables us to pinpoint its host galaxy. This, in turn, tells us the distance the FRB has traveled, a piece of information that is vital when using FRBs as cosmological probes, especially when combined with the concept of dispersion measure.
Dispersion measure sounds like a key concept.
It is.
Can you explain it in more detail?
When light travels through space, particularly through regions containing ionized gas, it interacts with the electrons present.
Okay.
These interactions cause a slight delay in the arrival time of the light, with lower frequencies experiencing a greater delay than higher frequencies. This frequency-dependent delay is what we call dispersion measure, or DM.
So it's like the light is getting stretched out with different frequencies arriving at slightly different times.
Right.
And the more matter the light passes through, the greater this delay becomes.
Exactly. DM is directly proportional to the amount of ionized matter between us and the source of the light.
Okay.
So by carefully measuring the DM of an FRB, we can estimate how much matter it has encountered on its journey.
Okay.
It acts as a cosmic ruler, helping us map the distribution of matter in the universe.
Now I'm starting to see how this all connects.
Yeah.
We have these powerful FRBs traveling billions of light years, and by analyzing their dispersion measure,
Right.
we can trace their paths and determine how much matter they've encountered. This information then helps us address the missing baryon problem, which you mentioned earlier.
You're absolutely right. By using FRBs to probe the otherwise invisible distribution of matter, we can potentially uncover the hiding places of those missing baryons.
This is where the McCourt relation comes in, right?
Yes.
Can you tell us more about this groundbreaking relation and what it reveals about the missing baryons?
The McCourt relation is indeed a groundbreaking discovery, and it underscores the potential of FRBs as powerful tools for cosmology.
Okay,
It establishes a correlation between the dispersion measure of an FRB and the redshift of its host galaxy.
got it.
Redshift, as you likely know, is a measure of how much the light from a distant object has been stretched due to the expansion of the universe.
Right.
The further away a galaxy is, the higher its redshift will be.
So the McCourt relation suggests a direct link between this redshift or distance and the amount of dispersion we observe in the FRBs coming from those galaxies.
Yes.
The further the FRB travels, the more matter it interacts with, leading to a higher dispersion measure.
Precisely. This relationship was first observed in 2020 by a team led by Jean-Pierre McCourt, hence the name. They analyzed a sample of localized FRBs and discovered that their dispersion measures aligned perfectly with the predicted values based on their redshifts and the estimated amount of baryonic matter in the universe.
Oh.
This revolutionary finding provided the first concrete evidence that a significant portion of the missing baryons reside in the vast spaces between galaxies.
Okay.
This diffuse hot gas, known as the warm hot intergalactic medium, or HRQIM, is challenging to observe directly, but its presence is revealed through the dispersion measures of FRBs.
That's incredible. We've gone from these mysterious fleeting radio bursts to mapping the distribution of matter across immense cosmic distances and uncovering hidden reservoirs of baryons. FRBs have transformed from an astrophysical curiosity to a powerful tool for unlocking the universe's deepest secrets.
They have.
But I have a feeling that our exploration of the McCourt relation and its implications for the missing baryons is just the beginning.
It is.
There's much more to uncover, right?
Absolutely. The McCourt relation is just the first step. Now we need to delve into the finer details of this relationship.
Okay.
Where are these missing baryons concentrated? How are they distributed within the intricate tapestry of the cosmic web?
Right.
What can this tell us about the universe's structure and its evolution? These are just some of the questions we'll explore as we continue our deep dive into the world of FRBs.
That's a perfect segue into the next part of our exploration, where we'll delve deeper into the distribution of missing baryons and the complexities of the cosmic web.
Sounds good.
Welcome back to our deep dive into the world of fast radio bursts.
FRBs.
FRBs. We've established that FRBs are powerful tools for probing the universe's matter distribution, especially the elusive missing baryons. The McCourt relation hinted at their presence in the vast intergalactic spaces.
Right.
But as you mentioned, it's only the first step. How can we go further and map these missing baryons within the cosmic web?
While the McCourt relation is a powerful tool, it provides just a glimpse into the complexities of baryon distribution. It confirms the presence of missing baryons, but doesn't pinpoint their exact locations or their arrangement within the cosmic web.
Okay.
To achieve that, we need to dissect an FRB's dispersion measure,
Okay.
understanding that it's not a result of a single uniform medium.
So it's about breaking down the dispersion measure into its components, like peeling back the layers of an onion to see the whole picture. What are some of these layers we need to consider?
Think of it as tracing the journey of an FRB signal from its source to our telescopes on Earth.
Okay.
The first layer is the contribution from our own Milky Way galaxy. Our galaxy filled with ionized gas, especially in its disk, and halo inevitably contributes to the dispersion measure of any extragalactic signal passing through it.
Okay.
After accounting for this, we delve into the extragalactic dispersion measure, which can be further divided into contributions from the intergalactic medium, IGM, the vast spaces between galaxies, and the halos of intervening galaxies that the FRB signal has encountered.
So we have the IGM and the halos of galaxies,
Yes.
each with its own unique properties and distribution. How do they differ in their contribution to the dispersion measure?
The IGM, thought to be a diffuse hot gas, traces the large-scale structure of the cosmic web, those filaments and voids that constitute the universe's skeleton. Its contribution to dispersion measure is expected to increase steadily, with redshift reflecting the increasing distance and the amount of matter the FRB signal traverses.
Okay.
On the other hand, galaxy halos, more localized and denser than the IGM, contribute to the dispersion measure based on factors like the halo's mass gas content and the proximity of the FRB's path to the halo's center.
So unlike the IGM, which has a more predictable contribution based on redshift,
Right.
the halo contribution is much more variable,
It is.
depending on the specific galaxies encountered by the FRB signal.
Yes.
It's like each FRB carries a record of its unique journey through the cosmic web.
Precisely. And this is where it gets exciting. By studying the dispersion measure contributions from both the IGM and galaxy halos,
Right.
we can construct a detailed picture of how baryons are distributed in the universe.
Okay.
We can even test various models of galaxy formation and evolution, which predict how gas is drawn onto galaxies and expelled through feedback processes.
So we're not just finding missing baryons, but understanding their interactions with galaxies and their role in shaping the cosmic landscape.
Exactly.
But how do we separate the IGM and halo contributions to the dispersion measure?
That's the challenge, and we are exploring several approaches. One is to rely on detailed spectroscopic observations of galaxies along an FRB's line of sight. By identifying and characterizing these galaxies, we can estimate their halo masses and gas content, allowing us to model their contribution to the dispersion measure.
It's like taking a cosmic census, cataloging the galaxies along the FRB's path to understand their individual impacts.
Exactly.
But what about FRBs that haven't been precisely localized?
Right.
Can we still glean information about the IGM and halo contributions from them?
Even with unlocalized FRBs, where the exact path is unknown, we can still extract valuable information by studying the statistical distribution of their dispersion measures.
Okay.
This distribution reflects the overall clumpiness of matter in the universe, the relative contributions of the IGM and galaxy halos, and the influence of galaxy feedback processes. It's like studying the texture of the cosmic web, how matter is arranged on large scales.
And to analyze this texture, we need to compare the observed distribution of dispersion measures to predictions from cosmological simulations, right?
Exactly. Cosmological simulations, which model the evolution of the universe, including galaxy formation and gas distribution, allow us to explore different scenarios for missing baryons and their impact on the cosmic web.
Okay.
However, it's important to remember that these simulations are complex and rely on our current understanding of physics and the universe's evolution.
So there's a level of uncertainty, a need to compare different simulations and refine our models based on what we observe with FRBs.
Yes.
The constant interplay between observation and theory pushing the boundaries of our knowledge.
Precisely. This dynamic between observation and theory is crucial for scientific progress. Now, shifting gears a little, we've discussed missing baryons in the cosmic web, but FRBs also offer insights into another cosmological puzzle, the Hubble tension.
Ah, yes, the Hubble tension, one of the most intriguing mysteries in cosmology.
Right.
It refers to the discrepancy between different measurements of the universe's expansion rate, the Hubble constant.
Exactly. We have measurements from the early universe based on observations of the cosmic microwave background and measurements from the late universe using techniques like the distance ladder method with Type Ia supernovae.
Right.
These measurements, however, don't quite agree, leading to this tension or discrepancy.
And FRBs offer a completely independent way to measure the Hubble constant.
They do.
How is that possible?
Remember the the correlation between dispersion measure and redshift.
Right.
This relation is sensitive to the Hubble constant. By analyzing a large sample of FRBs with known redshifts,
Okay.
we can use them as standard candles, similar to Type Ia supernovae, but with entirely different underlying physics.
So FRBs could act as a tiebreaker, helping us resolve the Hubble tension by providing an independent measurement of the universe's expansion rate.
Yes.
This is remarkable considering we started with these seemingly fleeting bursts of radio waves.
It is truly remarkable how versatile FRBs are as cosmological probes. And our journey through their applications doesn't end here. We've explored missing baryons, the cosmic web, and the Hubble tension, but FRBs also offer a window into another fascinating realm: cosmic magnetism.
Cosmic magnetism, a realm that sounds both mysterious and fundamental. How do FRBs help us understand this invisible force shaping the universe?
Cosmic magnetism is indeed one of the least understood aspects of the universe, yet it plays a crucial role in shaping galaxies, influencing star formation, and even affecting the large-scale structure of the cosmic web.
Wow.
These magnetic fields permeate space, often invisible to our conventional telescopes.
Right.
But we can detect them through their effects on light, particularly polarized light.
Okay.
And this is where FRBs come in.
Polarized light, where the light waves oscillate in a specific direction rather than randomly.
Right.
And cosmic magnetic fields can twist or rotate this polarization as light passes through them.
Exactly. This rotation of polarized light is called Faraday rotation, and it's directly proportional to the strength and orientation of the magnetic field along the light's path. FRBs, with their often polarized radio waves, become powerful probes of cosmic magnetism.
So by analyzing the polarization of FRB signals, we can map the magnetic fields they've encountered on their journey,
Yes.
revealing the invisible structure of cosmic magnetism. It's like gaining a new sense, allowing us to perceive the universe in a completely different way.
That's a great analogy. This measurement, the rotation of polarized light, is called the rotation measure, or RM.
Okay.
Similar to dispersion measure, the RM of an FRB reflects the cumulative effect of all the magnetic fields that has passed through from its host galaxy to the intergalactic medium to our own Milky Way.
But I imagine studying cosmic magnetism with FRBs presents its own set of challenges, especially considering the subtle nature of these magnetic fields.
You are right. Measuring the RM of FRBs requires highly sensitive telescopes and meticulous analysis techniques.
Okay.
We need to disentangle the contributions from different sources along the FRB's path, just as we do with dispersion measure.
Right. The rotation of polarization can be subtle, demanding precision and careful interpretation.
It seems like a delicate yet incredibly rewarding endeavor. What are some of the key insights we hope to gain from studying cosmic magnetism with FRBs?
One of the fundamental questions we hope to answer is the origin of these cosmic magnetic fields.
Okay.
Were they present in the early universe shortly after the Big Bang, or did they emerge later generated by astrophysical processes like star formation and the activity of supermassive black holes?
So it's a question of whether these magnetic fields are a primordial feature or a product of cosmic evolution.
Exactly.
And FRBs could hold the key to unraveling this mystery.
Exactly. By studying the RM of FRBs at different redshifts, we can essentially trace the evolution of cosmic magnetism over time, understanding how these fields have grown and shaped the universe we observe today.
Wow.
It's like looking back in time, witnessing the invisible forces that have sculpted galaxies, clusters, and the cosmic web itself. But our deep dive into the realm of FRBs has revealed yet another layer, another intricate phenomenon that these bursts can illuminate. Scattering.
Scattering is indeed another fascinating phenomenon that we can study using FRBs. It refers to how light, or in this case radio waves, can be deflected or scattered as they pass through a turbulent medium like the ionized gas in space. Imagine shining a flashlight through fog. The light gets diffused and scattered, making it harder to see the source.
So instead of receiving a crisp signal, the FRB gets spread out in time, its profile broadened or distorted by this scattering effect.
Right.
And this scattering can tell us something about the properties of the medium the FRB has traveled through.
Precisely the amount of scattering observed depends on the density and turbulence of the gas, as well as the distance the FRB has traveled.
Okay.
By analyzing the scattering properties of FRBs, we can gain valuable insights into the turbulent nature of the interstellar and intergalactic medium, those vast expanses of gas and dust that fill the space between stars and galaxies.
It's like using FRBs to study the weather patterns of the cosmos, understanding the turbulent flows and eddies of gas that shape the universe.
Yeah.
But I imagine this scattering can also complicate our analysis of FRBs. If the signal is spread out, it becomes harder to detect and study.
You're right, scattering can be a double-edged sword. On one hand, it provides valuable information about the interstellar and intergalactic medium.
Right.
On the other hand, it can make FRBs harder to detect, especially at lower frequencies where the scattering effect is more pronounced.
I see.
It's analogous to trying to listen to a faint whisper amidst a roaring wind. The signal is present but obscured by noise.
And to overcome this challenge, we require telescopes with high sensitivity and the ability to observe at a wide range of frequencies.
Exactly.
This allows us to capture the scattered signal and analyze its properties in detail. It's remarkable how every aspect of an FRB signal, from its dispersion measure to its polarization to its scattering properties, carries a wealth of information about the universe.
It is indeed remarkable, and it highlights the potential of FRBs as multifaceted probes of the cosmos. Now delving further into the nuances of scattering, we were just discussing how scattering, while providing valuable insights into the properties of the interstellar and intergalactic medium, also poses challenges to detecting and analyzing FRB signals.
That's true. Scattering can make it difficult to disentangle the intrinsic properties of the FRB from the effects imposed by the intervening medium.
Yeah.
However, it's this very challenge that pushes us to develop more advanced techniques and instruments,
Right.
leading to a deeper understanding of both the FRBs and the universe they travel through.
Absolutely.
You mentioned that scattering can help us distinguish between different types of cosmic environments.
Yes.
Can you elaborate on that?
Certainly,
Yeah.
the degree and characteristics of scattering can provide valuable clues about the density, turbulence, and composition of the medium through which the FRB has passed. For instance, if we observe an FRB with a high dispersion measure but relatively low scattering, it suggests that the signal has traversed a dense but relatively homogeneous medium, like the hot gas within a galaxy cluster.
You're right.
Conversely, high scattering coupled with a high dispersion measure implies a more turbulent environment like the gas found in star-forming regions or supernova remnants.
So scattering acts as a kind of fingerprint, helping us differentiate between various cosmic environments and understand the nature of the gas responsible for the observed dispersion.
Exactly.
It's another piece of the puzzle, allowing us to paint a more detailed picture of the matter distribution throughout the universe.
Precisely. And it's not just about the large-scale distribution of baryons. Scattering can also reveal details about the immediate surroundings of the FRB progenitor itself, the object that generates these powerful bursts.
That's fascinating. So we can use scattering to probe both the vast cosmic web and the localized environments where FRBs originate.
Exactly. Some FRBs, for example, exhibit extreme scattering, far exceeding what we would anticipate from the interstellar or intergalactic medium alone. This suggests something unique about their immediate environment, something that's causing this intense scattering.
Could this extreme scattering be a clue to the nature of the FRB progenitors themselves?
It's a strong possibility. One prominent theory proposes that some FRBs are produced by magnetars, highly magnetized neutron stars with incredibly strong magnetic
All
fields.
right.
Magnetars are known to be surrounded by turbulent magnetized winds, which could explain the extreme scattering observed in some FRBs.
So the scattering becomes a signature, a telltale sign of the turbulent environment surrounding a magnetar, providing further support for this progenitor model.
Precisely. This is just one example of how scattering can offer crucial insights not only into the large-scale structure of the universe, but also into the very nature of the FRD sources themselves.
It's remarkable how FRBs are illuminating so many different aspects of astrophysics and cosmology, from the distribution of matter to the nature of dark energy to cosmic magnetism and the properties of exotic objects like magnetars.
Yeah.
They're truly opening up new windows into the universe, revealing secrets that were once hidden.
And we've only just begun to explore the potential of FRBs. As we detect and localize more of these bursts, especially with the next generation of radio telescopes like the Square Kilometre Array, we'll be able to probe even deeper into the cosmos and unravel even more of the universe's mysteries.
It's an exciting time to be studying FRBs. They've transformed from a relatively unknown phenomenon to one of the hottest topics in astrophysics, with the potential to revolutionize our understanding of the universe. You've given us a lot to think about today regarding these fascinating bursts of energy. Could you leave us with a final thought to ponder?
Absolutely. Here's a thought-provoking question to consider. Could FRBs help us unlock the secrets of dark matter, the elusive substance that constitutes the majority of the universe's mass? We know that dark matter interacts gravitationally, but its nature and its interactions with normal matter remain a mystery. Could FRBs, with their sensitivity to the distribution of matter, provide us with clues about the distribution and properties of dark matter?
It's a tantalizing possibility, a glimpse into the future of FRB research, and the potential for these enigmatic bursts to unravel not just the mysteries of baryons and magnetism, but the very fabric of the universe itself. Thank you for joining us on this deep dive into the fascinating world of fast radio bursts. We hope you've enjoyed the journey and are as excited as we are about the future discoveries that await us.